This video is about invertible functions. Suppose we have a function f from a set A to a set B, and a function g from the set B to the set C. Then g composed with f from the set A to the set C is defined by saying that g composed with f of little a is equal to g evaluated on f of a for any little a in the set A. Another definition, if we have a set S, then the function I sub s that takes s to itself is called the identity function for s if it just takes every element of s to itself. In other words, for all x in S, I sub s of x is just x. Finally, suppose we have a function f that takes a set A to a set B. Then we say that f is invertible if there's another function, h, that goes backwards from B to A, such that when I take h composed with f, so that would be from A to A, that's just the identity function of A. And if I go the other direction and take f composed with h, so that would be taking the set B to B, that's just the identity function of B. Equivalently, I could say that for all little a in big A, h composed with f of little a is just itself. And for all little b in the set B, f composed with h of little b is just itself. The function h is called the inverse of f if this happens, and it's written as f to the minus 1. Intuitively, a function and its inverse undo each other. So when you apply one and then the other, you just get back to the start. So you might think of an invertible function as like putting on your shoes. There's a way to undo it, which is taking off your shoes. If you first put on your shoes and then take off your shoes, you're back to where you started. Or if you have your shoes on already and you take them off and put them on, you're back to where you started. So here's a simple example. Let's call this function f. It takes the numbers from 1 to 4 to the letters A, B, C, and D, according to these rules. If I want to do the inverse, f inverse, I have to go backwards and undo all of f's work. So f inverse would take A to 4, C to 3, B to 2, and D to 1. Notice that if I do f inverse composed with f, that's going to take the number 1 to D and then back to 1. It'll take 2 to B and then back to 2, 3 to C, back to 3, and 4 to A and back to 4 again. And if I do them in the other order, then I'll start with the letters. For example, A goes to 4 and then back to A. And in both cases, the composition just gives me the identity that takes every number to itself or every letter to itself. What about this next example? Is this function invertible? I could try drawing an inverse. So that would get me from y to x. For example, I'm probably going to want D to go to 1, B to go to 2, and say I take C to 3. And they call that map H. And I'll call the original map F. Now, if I do F composed with H, let's see, that's going to take C to 3 and back to C. It'll take B to 2 and back to B. And it'll take D to 1 and back to D. So F composed with H is the identity for my set Y. But look what happens if I do H composed with F. That'll take 1 to D to 1, 2 to B to 2, and 3 to C to 3, but it takes 4 to C to 3. So H composed with F is not the identity of X, and therefore H and F are not inverses of each other. In fact, there's no way to build an inverse for F because we have to make a choice for what C goes back to. And if it goes back to 3, then 4's going to end up going back to 3 when I do this composition here. And if I choose C to go back to 4, then 3 will go to 4 when I do this composition. So the answer is no, no inverse. What about the third example? Is F invertible this time? Again, I'm going to run into trouble. If I build my map H from Y to X, then it's easy to figure out where to send D and B and A, but I run into trouble when I get to C. Whatever I decide to send it to, I'm going to run into trouble when I do F composed with H evaluated on C, because this could never equal C again since F itself doesn't ever hit C. For example, in this case, F composed with H of C is equal to A, since we go to 3 and then to A. So this function is also not invertible. As you look at these simple examples, you might notice that this example fails to be invertible because F was not 1 to 1. And this function fails to be invertible because F is not onto. When F was a bijection, we were able to invert it. In fact, this is a general rule. F is invertible if and only if F is a bijection, both onto and 1 to 1. Let's prove this fact. Since it's an if and only if, we're going to have to do 2 directions. First, let's show that if F is invertible, then F is a bijection, 1 to 1 and onto, and then next we'll show that the other direction. If F is a bijection, then it's invertible. So let's start with this one first. So let's assume F is invertible. To show its bijection, we need to show first that F is 1 to 1, and then we'll also show that F is onto. To show that F is 1 to 1, suppose that we have A1 and A2 in A, the domain of F, such that F of A1 equals F of A2. They're going to the same place. We're assuming F is invertible, so let's let F inverse be F's inverse. Then we can apply F inverse to F of A1. That's going to equal F inverse of F of A2. But F inverse composed with F is just the identity function, right? So F inverse of F of A1 is just A1, and so A1 equals A2, which is exactly what we need to show that F is 1 to 1, right? We showed that if 2 elements of the domain get sent to the same place, then they were in fact the same element. Another way to say the same thing, the contrapositive, is that if we had 2 different elements, they couldn't possibly go to the same place. Now we need to show that F is onto, surjective. So let's suppose that we have some little b in the set B, and let's consider F inverse of little b. Well, F of F inverse of little b is going to be little b, right? That's what it means to be an inverse. And so that means that we found something in A. So there exists some A in A, where A is just F inverse of B, such that F of little a equals B, and therefore F is surjective, or onto, by definition. This completes the proof that F is bijective. Now let's go the other direction, and we'll show that if F is bijective, then F is invertible. So let's assume F is bijective, that is, it's 1 to 1 and onto. Remember that F is going from the set A to the set B. let's define an inverse function. For now, we'll call it h, and we'll show that it's the inverse after we define it. So we're defining h from set B to set A, going backwards, as follows. For little b in B, since f is surjective, there exists an A in A such that f of little a equals little b. In fact, this little a is the unique because if, say, A2 is in A with f of A2 equals b also, then since f is 1 to 1, A2 would have to equal A1. So we can define h of little b to be this A, right? This A is the unique element of set A such that f of little a equals b. And notice that we used both surjectivity and injectivity in this definition. So now we need to check that f composed with h is the identity function of b, and h composed with f is the identity function of a. For the first part, for a little b in B, recall that h of B is the unique A in A such that f of A equals B. And therefore, if I do f of h of B, I'm going to get B, right? This right here is the unique A in A such that f of A is little b, and when I take f to it, therefore I have to get b. So f composed with h is going to be the identity function. On the other hand, if I do h composed with f for some little a in A, h composed with f of little a, that's h of f of A. And by definition, this is the unique element of the set A that f brings to f of A. Well, little a certainly works. F brings little a to f of little a, so it must be b little a. So therefore, h composed with f of little a is little a, and so h composed with f is the identity of the set A also. And so h is the inverse of f, which means that f is invertible. In this video, we gave some examples of simple functions that were invertible or not invertible, and we showed that a function is invertible if and only if the function is a bijection.